Okay, let's get this started. How's everyone doing? Feeling a little chilly here today in San Jose. This is according to my colleagues in the area. But coming from New Hampshire, this is just a normal temperature for us. Over there back home, it's getting a little chilly. We're going to talk about something pretty cold, even colder than that. So about quantum computing and how that actually tied together. So hello everyone, my name is Yang Yu. I'm the Applications Engineering Manager at Amphenol Ardent Concepts. Once again, we're here at OCP today, excited to share with all of you what we're observing in quantum computing applications and implications on system-level interconnect designs. In the next 15 minutes or so, we'll go over the microwave cabling challenges and the solutions involved in scaling today's quantum computer.
We need to have your slide went black.
Okay. Is it going? Oh.
Can you try to port it out again?
Is the port?
Because right now we don't have anything. If you
Okay.
right now we have your desktop now.
Okay. Well, let me get the graphics back up. Yep. Okay, we're back. Okay, so let's get back to it. Today's quantum computers are also known as noisy intermediary scale quantum, which is named so because it's a step between the very early on experimental quantum computer and the future large-scale fault-tolerant quantum computer that's promised to deliver quantum advantage at commercial scale. Although some of the latest algorithms and software development have shown promising improvements on improving fault tolerance, but from an interconnect and hardware perspective, sensitivity to thermal and electric noise still poses as a challenge. And to combat these noise challenges, quantum processor units, or QPUs, typically housed in the delicate qubits, are typically encased within vacuum chambers and cooled to millikelvin temperature using dilution refrigeration technology. Incidentally, millikelvin temperature, that's just a millikelvin above absolute zero, the coldest place in the universe. So coaxial cables are still the predominant medium that carry the inputs and the readout signals to and from the QPUs. And it's also a vital component when noise reduction is considered within the quantum systems. The future large-scale quantum computer also calls for qubit counts that are exponentially larger than what's available today. So to reach that holy grail, that presents both development and hardware challenges, notably in scaling microwave RF lines. And that the ideal solution must balance between mechanical density, signal integrity, as well as a thermal consideration for the overall system success. Now, if we explore the inner workings of a quantum computer, we find critical hardware components that enable practical installation and adaptability to evolving architectures. While not explicitly depicted in this illustration, quantum computers critically rely on abundance of control electronics, and typically housed in a rack and stack configuration at room temperature, will serve as controllers for all the qubits and the signal processors, as well as interfacing with any sort of cloud service infrastructure. But right now, today, our focus is more on the inside. So while these control electronics come in variable form factors, from modular PXI-E style cartridge design to all the way to highly customized front panels, all of those solutions are also geared toward maximizing RF connection points. Establishing microwave RF connections within the quantum computer relies on specialized hermetic RF feedthroughs. And these feedthrough components maintain the necessary vacuum levels inside the cryogenic chamber while serving as impedance-controlled electrical transition points. As we move closer to quantum processor units into the fridge, we now encounter both passive and active microwave electronics. For instance, the cryogenic attenuators filter RF signals and assist in thermalizing the coaxial cables at each stage of the dilution refrigerator. And finally, our RF signals must also interface directly with or near the QPUs, necessitating the most compact and efficient solution. These intricate components work together to facilitate the quantum computing process. Quantum computer systems of today use coaxial cables for microwave RF connections. often employing traditional pin and socket coax-based interfaces. To ensure hermeticity, the electrical feed-through must include an epoxy or glass sealed provision between the standard conductor, dielectric, and a connector body. The connector body must also maintain helium leak-tight integrity to the feed-through flange. In the image on the left, we see a hermetic electrical feed-through solution based on an O-ring sealed bulkhead SMA connector within a standard ISO 100 flange. However, SMA-based hermetic solutions have limitations and require generous clearances for tools such as torque wrenches necessary for installation, as well as removal of coaxial cables. Modern quantum computing architectures require much greater signal density, therefore favoring a GaN approach, eliminating housing and tooling clearance constraints. So the advanced GaN hermetic electrical feed-through shown on the right represents a substantial density improvements over the traditional SM8 or SMP technology. Quantum computing systems in the realm of quantum computing, the transmission of RF signals to and from the quantum processor is a critical process demanding the utmost in-noise control. This calls for effective filtering and thermalization throughout the application of attenuator circuits. The circuits often offer tunable filtering capabilities, effectively reducing noise while also ensuring proper thermalization of the RF coax cables. This is especially important for the center conductor of the coax, which otherwise would be thermally insulated by the dielectric layer throughout the transmission line. As with the hermetic feed-through, traditional attenuator circuits rely on SMA or SMPM form factors. However, as we push the boundaries of the quantum computing, attenuator architecture requires a greater density than what is available with traditional coax technologies. Again, a GaN approach can provide superior density through eliminating many of the mechanical bottlenecks associated with SMAs and SMPMs designs. The GaN attenuator design shown above here can achieve an unmatched 2.54 millimeter by 3 millimeter signal density in a tunable format, meeting the requirements of a modern quantum computing system. When we examine the intricate hardware architecture of a quantum computing systems, we encounter a critical constraint at the RF launch points near the quantum processor units themselves. These launch transitions at a QPU must meet extraordinary demands, including exceptionally high level of electrical isolation over a range of RF substrates. Moreover, the connectors mating to the QPU must also endure the lowest and the most extreme temperatures at millikelvin above absolute zero. To tackle the electrical and the cryogenic challenges, many quantum engineers have embraced solderless compression mount connector technology. This innovation provides a solder-free and electrically compliant connector and launch transition, ensuring reliable mechanical integrity in the most frigid millikelvin environments and through multiple thermal cycles as well. Solderless compression mount technologies offer the added advantage of facilitating faster swapping of a QPU architecture as well, while reducing the overall QPU cost by eliminating the need for additional board-mounted connectors. As with the previous components we have reviewed, a GaN approach induces the highest level of density, particularly in the dimensionally constrained region of near the QPU. With quantum computing still in its infancy, RF connections to and from the QPU still must accommodate a wide range of QPU form factors and substrate materials. This is made possible through a wide array of channel counts and mounting form factors, allowing designers to position connectors as close to the quantum processor as possible. GaN solderless connector solutions represent an indispensable technology in our pursuit of achieving density and performance that's needed to meet the demands of exponentially growing qubit counts and in the future chip-to-chip communications. Now, by establishing a comprehensive GAN coaxial ecosystem, encompassing solutions ranging from room temperature control electronics to hermetic feedthroughs, attenuators, intermediate wirings, and QPU mount options, quantum computing designers now can effectively scale qubit counts without encountering bottlenecks at hardware transitions. System designers seeking the greatest density possible can adopt a holistic system-level approach by leveraging the all-encompassing GAN ecosystem, also known to us as the top-to-bottom approach. The GAN ecosystem shown here is designed for immediate integration with mainstream cryogenic dilution refrigerator system. Today, such a GAN ecosystem are commercially available with 2.54 millimeter signal-to-signal pitch with 1.9 millimeter coaxial versions in beta testing right now. And as application requirements continue to evolve, we're looking at even more microwave components such as filters, amplifiers, and couplers will start to also be incorporated into this high-density GAN approach as well, just like the attenuators. And in development of all of these individual interconnect components culminate in a full fridge high-density wiring system, like the example shown here. This example, the compressive solution starts at a hermetic feed-through and include the wirings and microwave components connecting at each stage at a dilution refrigerator. To ensure the best user experience in this critical and complex system, a wiring solution like this will be custom designed to be mechanically installed in one piece within the specific fridge that the quantum computer deploys. While the individual components remain modular and easily accessible for service, they're pre-installed on a custom-designed mounting fixture and rigs, fully validated electrically and hermetically tested prior to shipping. This approach minimizes any risk associated with shipping, handling, and for users first install. And this may yet be another overlooked benefit because the GAN form factors and the system level approach should drastically reduce the amount of time the quantum engineers and physicists have to spend hands-on with the quantum computer's interconnect side, and consequently freeing up more time for them to focus on other critical areas of quantum computer development. While the majority of this presentation have emphasized on the density improvements achieved through GAN coaxial systems, the future of quantum computing demands even greater densities than coaxial cable alone can achieve. As quantum systems evolve to become more fault tolerant, the performance offered by coaxial cables may no longer be needed. In the pursuit of a truly commercial scale quantum computing ecosystem, reducing the hardware cost is paramount. Relying solely on coaxial cables is financially impractical, given the required number of qubits for commercial quantum computing. At the core of a GAN coaxial solution, showcased today, lies a dual-sided compression interface. This interface design is capable of delivering the necessary level of electrical and mechanical performance independently without complete reliance on coaxial cable. And consequently, a variety of transmission lines can be integrated with this interface, enabling greater densities than coaxial cables can achieve, and potentially offering more cost-effective solution. And the chart presented illustrated here compares some of the leading transmission line technologies under investigation as suitable mating architectures for the existing solderless mount interface. And while deploying non-coax-based solutions such as a flexible printed circuit presents numerous challenges, our investments in cryogenic development infrastructure and our long-standing focus on RF design provide us with optimism that a solution can be realized through time and effort in the future. Lastly, today, just as a summary, we've delved into a crucial part of quantum computing, the microwave RF transmission line. We've explored how coaxial cables excel in providing the best electrical performance for noisy intermediate scale quantum system. But as the qubit counts increase, we face unique challenges. First, scaling up qubit counts means scaling up the density of supporting components, including coax cables, hermetic feed-throughs, and as well as attenuators. And the concept of a GAN form factor, such as TR multi-coax, allows us to achieve a coax densities down to an impressive 1.9 millimeter signal-to-signal pitch. And when incorporated into comprehensive wiring solutions such as CWS, it also alleviates the concern of a complexity and a reliability associated with ever-increasing number of lines and components. In the future, quantum computing will demand more RF channels and density than traditional coax can provide. The RF transmission lines of the future quantum computing ecosystem will be a marriage of a density, signal integrity, and cost effectiveness. And thank you very much.